Hello everyone, welcome to my video on the definite integral. This is one of the most important notions of Cal 2, so make sure you're paying attention and you understand this concept. So everything we've done up until now in the Cal 2 series has built to this moment here, and everything we're going to do after this video is based off this definition here. So this idea of cutting up or partitioning an interval into n equal subintervals and summing up the parts is it's a notion, it's an idea that we're going to keep reapplying throughout the semester, okay? So make sure you're comfortable with that. So let's go ahead and look at the definition of a definite integral. So the definition over here says if f is a function defined for x on a closed interval ab, we partition the interval into n subintervals of equal length using this formula here, which we've already seen. Delta x equals b minus a over n, so we're cutting it up into n equal subintervals. We let a equal xo, x1, x2, xn minus 1, and we end at xn, we call that b. So we're starting at a, which is xo, and we're finishing at xn, which we call b. These are the endpoints of each subinterval, and we consider sample points. So sample points, these x1 star, x2 star, all the way to xn star, are values in between the intervals. So the xi star lies within our interval. Each subinterval that we created, in that subinterval we choose a sample point, and we're making the interval so small that we could choose any value in that interval and it won't affect our final answer. So that's the idea of choosing sample points, just to make this more general. Then we could define the definite integral f from a to b as this. So make sure you have this written down. I'm calling this not just the area, the net area. I'll explain why later. And the symbol we're using is the integral sign. So this looks like an S symbol, but it's essentially like stretched out. So it's like an S but stretched. So we have the integral from a to b. So we have a lower bound a, we have an upper bound b of the function f of x that's given dx. So whenever you have an integral sign, it's packaged with a dx. These guys go hand in hand, they go together. And this is equal to our limit that we've seen in previous videos. So the limit as n tends to infinity of the summation of I equals 1 to n of f of xi star times delta x. So this was the idea of finding the area of each small rectangle. We take the partition, we cut it up into n subintervals, creating little rectangles, and this is allowing us to find the area of each rectangle and summing them up. And the limit as n goes to infinity is just taking the interval to be as small as possible. Okay, so provided that this limit exists, then we have this integral. We call the function integrable if this limit exists. Okay, so let's go ahead and look at an illustration of what this is telling us. So the geometric interpretation of the definite integral is we're approximating the area under the curve of this function f of x. So we have this green function here, f of x, and we're creating these small little red rectangles to approximate the entire area under the curve. Okay, so we took the interval because f is defined on the interval from a to b. We took that interval from a to b and we cut it up into n subintervals, so we split this guy up. And we found that a is x0, x1, the distance from x0 to x1 is delta x, right? So that's the width of, let's say, the first rectangle. And we spoke about these sample points, these x, let's do it on here. Let's go on the first one, x1 star. So we said xi star is between xi minus 1 and xi. So if we're talking about x1 star, this is an x value that lies between x0 and x1, so somewhere over here. Okay. And this y value here, since the interval is so small, it closely resembles the green function over here. So the y value that's associated to any point on this interval from x0 or the a to x1, its y value, its associated y value is going to be really close to the height of the function. So this is why we take sample points. We could choose any point that's on that interval. Okay, so we find the area of each term. So the width would be delta x, the height of the first rectangle would be f of x0 or f of x1 star, doesn't matter which one you choose, and the width would be delta x. Okay, and then adding all these up and taking the limit as n goes to infinity gives us an approximation for the area under the curve. This is the idea for the definite integral. Okay, so remember, when we're talking about definite integrals, we're going to see indefinite integrals later. When we talk about definite integrals, we're talking about a number, the area under the curve, which is a value. Okay, so we'll keep that in mind. So let's look and analyze the notation. So here I wrote the definition of a definite integral. I wrote it as the net area is equal to the integral from a to b of f of x dx, which is equal to the limit as n goes to infinity of the sum of I equals 1 to n of f of xi star times delta x. So this part here we just explained. We saw that f of xi star was the height at the sample point xi star. So at any xi star in the interval, we took f of xi star, giving us the height. Delta x we saw was the width of the rectangle. And we know that length times width, or height times width, is equal to the area of a rectangle. That's one of them. We're going to sum all of them up. And once we do that, we take the limit as n goes to infinity to make the width of the rectangle as small as possible. And at the same time minimizing our error, which gives us a better approximation. So this part here, we get it. We understand this. Okay. What I want to focus on next is the net area. Why am I emphasizing on the word net? The reason being is if we consider the function, this green function here, let me draw it in green, something like this. So it's always on a closed interval from a to b. This is a, this is b. Well, the reason why I'm saying net area is because this region over here, let's do it in green, because it lies above the x-axis, this is going to give us a positive answer. Okay, this is a positive answer, yet this value here lies under the x-axis. Oops. Let's put a big plus here. And that's going to result in a negative area. Because it's lying underneath the x-axis, this region here, the area under the curve is in the negative section. So this here is going to be negative. So why am I emphasizing on this? Well, because we're not talking about area, because we know that area can't be negative. But in terms of definite integrals, we're talking about net area. So if the function is mostly underneath the x-axis, then it is possible to have a negative answer, okay? So keep that in mind, very important. So that's why I put net in brackets. So this is net area, this is what we're talking about. So underneath the graph, we get a negative answer. A big minus sign over here. And now let's look at the notation of the integral sign. So we said the integral symbol is the limit of the sum. So we said s is sum, and we're essentially stretching the s, and it gives us this symbol. So I just want to write some terms here. So let's focus on just the integral sign now. F of x dx. Okay, so first of all, I mentioned that this symbol here, this elongated s, is the integral sign. This is the integral symbol. It's we're talking about the limit of a sum. So sum is the letter s, and you're taking its limit, so you're like stretching it out. This is why we get a stretched out s symbol for the integral sign. What's important here is you have your a, which is the lower limit or the lower bound. Oops, lower bound. A is b is the upper limit or the upper bound. And f of x is the function that we're integrating, and dx, I mentioned earlier, always goes with the integral symbol. So this is telling us that we're integrating with respect to x. It's the variable we're using. So integrating with respect to, so I'll abbreviate it WRT, with respect to x. This is the variable we're integrating with respect to, and f of x is the function, which the function inside the integral sign is what we call the integrand. Okay, but really just have to know the integral sign, lower bound, upper bound, or lower limit, upper limit, and the dx. Dx, delta x, is essentially this piece of the puzzle. Delta x and dx is over here. F of xi is essentially the function, and the limit of the sum is the integral sign. Okay, so this is the notation for the for integrals. Okay, and we know it's definite because the bounds are defined. So whenever we're dealing with definite integrals, you have your a and your b, you have numbers in the bounds. If you didn't have this, we're going to see this later on, this is called an indefinite integral. So without the a and the b, it's an indefinite integral. and there when we integrate those functions, we get a class of functions. Here, when you have a definite integral, we get a value because we're talking about area. Okay, so make sure you understand the difference, but we'll talk about this more later on when we start talking about indefinite integrals. Okay, so for definite integrals, this gives us a value, which is specifically the net area. Okay, so let's look at a couple of examples. So before we get to some examples, let's quickly take a look at this theorem over here, which states that if f of x is integrable on the interval a to b, on the closed interval a to b, so the integral exists, then the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation from 1 to n of f of xi times delta x, where delta x is b minus a over n, and xi, we've seen this already, is equal to a plus I times delta x. So this is stuff we've seen already, we're just going to apply it now. So we're essentially just using Riemann sums. So this is the limit definition of an integral, okay? So let's go ahead and look at the examples and apply this. So in our first example over here, it says to evaluate the following integral using Riemann sums, or using the limit definition of an integral. So why does it say that? Well, you might have learned FDC part 2, the fundamental theorem of calculus part 2, and it would be a lot easier to apply that at this stage, but in this series of videos we haven't seen that yet. So do not apply FDC part 2 for this example. You could check your work using FDC part 2, but really if it tells you to use the limit definition or using Riemann sums, you have to follow the question, answer it in that form. Okay, so we're using the limit definition. We're using Riemann summations. We're not using FDC part 2. So what do we know about what's given? Well, we know the lower bound is a, so 0 is a, and we know the upper bound b is 2. And we know 4 minus x squared. This is the function. This is what's in the integrand is the function. So the function we're dealing with is 4 minus x squared, and we're integrating with respect to x. Let's write this as a limit. We know this is the limit as n tends to infinity of the summation from I equals 1 to n of the function of xi. You could put a star, but I'm not going to put it, times delta x. So what we really need is delta x and xi. F we know the function, and we know a and b. So let's go ahead and get our xi and delta x. How do we do this? Well, we know that the formula for delta x. Delta x equals b minus a over n. So we know b is 2 and we know a is 0. So we have 2 minus 0, and we don't know n. They didn't tell us how many rectangles they wanted us to partition this integral in, or to estimate the integral, the area under the curve. So since they didn't give us the number of rectangles, we assume it to be n, and delta x is equal to 2 over n. Okay, so delta x is done. Now what we have to do is go get our xi. Again, we use the same formula that we've seen earlier when we did Riemann sums. Xi equals a plus I delta x. A is the initial value, or sorry, lower limit of the integral, which is 0. And delta x we just found. I is the index, delta x is 2 over n. This tells us that xi is equal to 0 plus I times 2 over n. Okay, so we have this and this. Good. So this limit up here, this is work we do on the side. Everything in here, this is side work. Once we found these values, we continue from the limit. So we're continuing from up here to limit. So we have the limit as n tends to infinity, summation I equals 1 to n. The function is this. So we have 4 minus, but instead of x, we're going to replace it with xi. And what is xi? Xi is simply just 2i over n. So we're substituting 2i over n into this function. So we're going to write it as 4 minus 2i over n squared. Okay, so instead of writing x, we're writing what xi is. What's xi? Xi is 2i over n, and that's going to be squared, and we're doing 4 minus that answer squared. 4 minus that answer squared. Okay, and then all this times delta x. But I'm not going to write delta x. What's delta x equal to? 2 over n. So this thing times 2 over n. Okay, so we have it in this form. Then now let's go ahead and evaluate this limit. So I'm going to distribute the 2 over n, and I'm going to simplify what's in the bracket at the same time. So limit as n goes to infinity, summation I equals 1 to n. 2 over n times 4 is 8 over n. And 2 over n times 2i over n squared is 2 squared is 4 times 2 is 8. I squared. N squared times n is n cubed. And this is what we have. Now to evaluate this, we could deal with the summations of each term individually because it's separated by a subtraction. So we can take the sum individually. So we have the sum from 1 to n of 8 over n minus the sum from 1 to n of 8i squared over n cubed. Okay, so I'm just going to have to erase to give myself some more room. Let's move all this. And we'll move all this. And let's continue up here. So this continues up here, equals to the limit as n goes to infinity. Over here, we just care about i's. So since there's no term that has an I, we could treat the 8 over n as a constant. So we could pull it out, leaving us with 8 over n times the summation from 1 to n of just 1. Right? If I multiply this back in, I get what I started with, so that's okay. Minus, again, everything that doesn't have an I, I'm going to factor out. So I'm going to remove the 8 over n cubed. And we're left with the sum from 1 to n of just I squared. And these are formulas that we have memorized. We know these guys. Okay. Give myself a bit more room. So keep writing the limit in the front, don't forget that. So the limit is actually attacking both these terms. And we know the sum from 1 to n of 1 is simply just n. We do 1 times n, giving us 8 over n times n, minus 8 over n cubed. And we know the formula for I squared, it's n times n plus 1 times 2n plus 1. All that over 6. Okay. So here the n's cancel, leaving us with just 8 minus, and I'm just going to take the limit and bring it on this side. I'm taking the limit of both terms, but since the first term we're just left with 8, there's no n involved, so it's just going to be 8. And here on the right side we have the minus, I'm taking it out, limit as n goes to infinity. We have 8 over 6, which I can write as 4 over 3. An n on top here, which cancels with one of the exponents, leaving us with n squared on the bottom. So 3n squared. And here we can distribute this whole thing, these binomials. So n times 2n is 2n squared. N times 1 is n. 1 times 2n is 2n. And 1 times 1 is 1. Okay. But again, all we really care about is the first term, because we care about the highest exponents. So here the highest exponent that we have, if we distribute the 4, the highest exponent is n squared, and 4 times 2 is 8. So the coefficient of n squared, because these values are smaller, we don't really care about them, and we care about the exponents that match, because those are the highest. Since they're equal, the answer is just the coefficient, so we're left with just 8 over 3. So we're taking a bit of a shortcut, but this is one of the shortcuts you could take. When the exponents match, you take the coefficients in front, okay? So we've seen this in earlier videos. If you don't believe me, what you could do is simplify this further, factor out an n squared from the numerator and the denominator, and you'll end up with the same result. You'll get 8 over 3. Okay. Here we find the common denominator, so we think of it as 8 over 1. We're subtracting fractions, so we can multiply here the left fraction by 3 on the top and the bottom, giving us 24 over 3 minus 8 over 3, which is 16 over 3. We're talking about area, so it's units squared, and this is the answer. Okay. So let's go ahead and look at another example. So the next example that we have, again, evaluate the following integral using Riemann sums, or using the limit definition of an integral. We have the integral from -3 to 0 of x minus 2 times x plus 4 dx. So we're integrating with respect to x. So pause the video, try and see if you could do this on your own. Okay. So the first thing that I would do to solve this is I would change its form. That's the first thing that's bothering me. We don't know how to integrate two terms that are multiplying, so we could just distribute our terms and deal with each term individually. So this is really the integral from -3 to 0. X times x is x squared. X times 4 and -2 times x leaves us with plus 2x, and -2 times 4 is -8 dx. Okay. But we're going to use our limit definition because we're using Riemann sums. Again, you cannot apply FTC part 2. It's telling us to use the limit definition. So let's go ahead and do that. The limit definition is the limit as n goes to infinity, the summation from 1 to n. The function that we're dealing with, this is f of x, everything here. And the lower bound is -3, the upper bound is 0. So b is 0, a is -3. So we have f of xi times delta x. Okay. Let's do this in red maybe, just to make it a bit more apparent. The lower bound here is a, the upper bound is b. And this whole thing is f of x. Okay. So let's go ahead and find our xi and our delta x. That's usually how we start these problems. Again, this is side work. So on the side of the sheet, we have that delta x equals b minus a over n. Always write down your formulas. We know our b is 0, our a is -3. So we have 0 minus -3. Be careful with your negative signs. Again, they didn't tell us anything about the number of rectangles we're going to partition the integral with, so we assume it to be n. 0 minus -3, be careful. It's positive 3 over n, not -3. So that's our delta x, and now let's go ahead and find our xi. Xi is equal to a plus I delta x. We know that a is equal to -3, so this is -3 plus I times delta x, which we just solved for is 3 over n. Okay, so this is our xi. So to solve this, what we're going to do, let's move this. We're going to write this limit as the limit as n goes to infinity, summation I equals 1 to n. The function that we're dealing with is up here, and we're replacing all the terms in here, replacing all the x's with xi. But what's xi equal to? Maybe I could do this in 2 steps and write f. Xi is just -3 plus 3i over n times delta x. So you're substituting all the x's in our function, because our function that we're dealing with, f of x, from up here, it's in the integrand, is x squared plus 2x minus 8. You're substituting all the x's in here with what's in the bracket here, -3 plus 3i over n. Okay, so we're going to get a large value. What we get is limit as n goes to infinity, summation I equals 1 to n. What we get is -3 plus 3i over n, all this squared, because the first term is squared, plus 2 times, instead of x, we're writing what's in the bracket again, -3 plus 3i over n, minus 8. And all this multiplied by delta x. And we know delta x is 3 over n, so times 3 over n. Okay. And now we have to go ahead and simplify this. Okay. So let's go ahead and do that. So distributing this, we get the 3 over n, I'm treating it as a constant, so I'm going to pull it out. I like to pull it out early, not to worry about it until the end. But it's up to you. So we get the limit as n goes to infinity, 3 on n times the summation I equals 1 to n. So I pulled out this 3 over n, and let's simplify this. So -3 times -3, this is a binomial squared. You're multiplying this by itself, so we have to FOIL. That gives us 9 minus 9i over n minus 9i over n plus 9i squared over n squared. So you distribute this by itself, you get this term. Multiplying into 2, we get -6 plus 6i over n. Okay, distributing 2, then -8. All this is in the square brackets. Okay, simplifying what's in the square brackets, what do we get? I'm just gonna have to erase and give myself some room. So let's erase up here. And let me just continue up here. The limit as n goes to infinity, we still have the 3 over n, that's here. And we have the sum, which is attacking all these terms. So the only term with an I squared is this. So we have 9i squared over n squared. If we look at the i's, we have -9i over n, minus 9i over n, minus 18i over n, plus 6i over n. So we're at -12i over n. So this, and this is done. And then we have 9 minus 6, which is 3, minus 8, which is -5. Okay. So we have this. So at this stage here, I would probably introduce the 3n, distribute it to all the terms, as well as the summation sign. So you don't have to solve it this way, this is just the way I'm doing it. So we have the sum from 1 to n. 3 times 9 is 27, I squared over n times n squared is n cubed, minus, I'm going to take the sum again. 3 times 12 is negative 36, I over n times n is n squared. Oh, sorry, I already took into consideration the negative, so this is going to be positive, okay? And then we have minus 5, so minus the sum from 1 to n. 5 times 3 is 15, so we have 15 over n. Okay. So again, at this stage here, we deal with each summation individually, and all we care about for the summations are all the terms that have i's in it. Anything that doesn't have an I, we treat it like a constant and pull it out. So we'll pull them out for all the terms, giving us limit as n goes to infinity. So make sure you keep writing your limit in the front, that's super important. Factor out the 27 over n cubed on the first term, or the first sum, leaving us with the sum of I squared. This, we know what this is. Minus, here I'm going to factor out 36 over n squared. Well, not factor out, just remove it, treat it as a constant. Sum from 1 to n of I. Again, this we know. Minus 15 over n, there's no i's here, so I'm going to take out the whole thing, leaving us with the sum from 1 to n of just 1, which again we know. So having our formulas memorized, we saw this in previous videos. We know this is equal to the limit as n goes to infinity, 27 over n cubed. The sum of I squared is n times n plus 1 times 2n plus 1 over 6. This is minus 36 over n squared. We know the sum of I is n times n plus 1 over 2. And we know the sum of 1 is just n. So we have 15 over n times n, okay? And we're taking the limit of all these terms individually. But here, the last one, we're just left with, the n's cancel, we're just left with minus 15. That's easy. As you can see, the question is long, so if you could take shortcuts, I don't mind it at this stage. But let's continue up here. The shortcut that we're going to do here is we're going to notice that the n times n is n squared. If we distribute this n, we get n squared plus n. So let's write that like that. We get n squared plus n. And all we care is, we care about the terms with the highest exponents, okay? So here we have an n squared, here we have n squared. What's the coefficient of n squared? Well, if you multiply with 2, on the bottom we have 2. And on the numerator, if we distribute the negative 36, we don't care about this term with the n because the exponent of n squared is larger. And since the exponent of the larger numerator and the larger denominator are equal, we know the answer is just simply the coefficient. So we have negative 36 divided by 2. Okay, so we still didn't do the first one. We know the second limit here was negative 36 over 2. And we know the last one was just minus 15. Let's go ahead and do the first one. Again, if you want to simplify and distribute everything, you could do it that way. I'm just looking at the highest exponent. So I know by multiplying n times 2n, that gives me the highest exponent. We'll get n cubed, and on the bottom we have an n cubed as well. So here, the coefficient would be 27 times 2, which is 54, over 6. So I'm skipping a couple of steps, I'm taking the limit, but if you do it the proper way, you distribute all the terms, or if you want to cancel like this n with an n, one of the n cubes, you have n squared on the bottom. Here you could distribute and take the limit by factoring out an n squared on the top and the bottom. Again, you'll get the exact same answer as I have. You'll end up with 54 over 6. And we know 54 divided by 6 is 9, minus 36 divided by 2 is 18, minus 15. Okay. 9 minus 18 is minus 9, minus 15. And that gives us minus, what is that, 24 units squared. Provided I didn't make any silly mistakes. Yeah, that's fine. So we get a negative answer. We have negative 24 units squared. Again, we're talking about net area, so this is fine. Okay. This is the final answer. And we're done up here. Okay. So as you can see, the questions are very long. So if you could take shortcuts over here, like I said, I don't mind it. By looking at the highest exponent and noticing that if the exponents of the numerator and the denominators match, when you're taking the limit as n goes to infinity, you're just going to get the coefficient, okay? Let's move on and look at our final example. So in the next example, it tells us to express the following integral as a Riemann sum. So again, we're going to express it as a limit. And now we have the integral from 0 to pi of sine of 2x dx, okay? So do not evaluate it, just express it as a limit of a Riemann sum, okay? So using our definition, we know this is the limit as n goes to infinity of the summation from 1 to n of f of xi times delta x. Okay, this is just definition. This again has to be memorized. And we know our lower bound is a is 0, and we know, a bit confusing, our upper bound is b pi, and our function that we're dealing with is sine of 2x. Okay, and again, we're integrating with respect to x. So let's go ahead and find our xi and our delta x. The formula that we're using is delta x equals b minus a over n. We know b is pi, a is 0, and n we don't know, so delta x is just pi over n, and then we could go get xi. Xi is equal to a plus I delta x. A is the lower bound, which is 0, plus I times delta x. Delta x is, we just solved for it, is pi over n. Okay, so we found our delta x and we found our xi. Now we substitute it into our formula. So this is equal, again, this is side work. This is equal to the limit as n goes to infinity, the sum from 1 to n. The function that we're dealing with is sine of 2x. So we have sine 2 times x. X is really xi, and xi is equal to I times pi over n. So this is just 2 pi I over n. Okay. So the 2 comes from here in the function. X is replaced with xi, and we know xi is, the 0 doesn't matter, it's just I times pi times n, over n. So we have 2 times I times pi divided by n. I put my constants in the front, that's just the notation I use, but we're just substituting this into the x. That's essentially what we're doing. And then we multiply by delta x, which we found was pi over n. Okay, and this is the answer. If you want, you could substitute, or you could factor out the pi over n, or remove it from the sum. The sign, you can't remove it because it has an I in it, so we can't evaluate this further. We're stuck at this point at this stage here. Later on, we're going to see how to evaluate these, okay? So this would be the final answer. This integral expressed as a limit of a Riemann sum, okay? So here we're done. So I hope this video helped. I hope you guys have a better understanding of definite integral and applying the limit definition of a definite integral. And we'll keep practicing. I'll see you in the next one.